Okay, so now let's talk about the other side of the curve where the number of infections are going down. So we're actually seeing a decrease in the number of people who are getting infected and a decrease in the total number who have that infection, which is what we're hoping to see over the course of the spring here so we can get rid of our social distancing rules and things like that. Um, and so, first of all, imagine if one infected person infected one more person. So it just basically stayed constant. Up here, that's basically what's happening as we see these curves flattening. So you can see China did that a while ago because that's where it started. So it reached that point sooner, and they were pretty strict about their isolation to keep it from spreading. And eventually, then you would hope to see that the number of cases would go down. And if you don't have new infections, and then the infections that do occur, if people are getting better, you would see the number of infections actually starting to drop. So I represented the little infected people with red dots here, but basically what that would mean is since you can't have one person infect less than one person, think of it more as like if you had four infected people, they would only pass on that infection to three people. That would show a reduction, or even better, if you had two infected people and those two only produced one infection, so it would cut it in half at every round, or if you had a big group of like 10 people, this would be a huge drop. Out of 10 people with the infection, they only pass that group of people only passes it on to one more person. And so that would show a really, really steep drop. So I started the pattern here, and hopefully you finish that pattern. I'm going to show it in Desmos. Again, okay to use Desmos. So your data would look something like this. So you can see the slowest one is the green one going down from 80,000, the city of Bellingham, and dropping slowly. It would take quite a few rounds, depending on how long a round is for COVID. It's a week or two, seems. It would go down kind of slowly. It would take quite a while. With a little bit more aggressive social distancing, or maybe some kind of treatment or a vaccine, or testing to help people isolate themselves, you could make that drop a lot faster. So the purple points cut in half every time, or the black points um, having 1/10 the number of infections after every round, it would drop off pretty fast. That would be nice, maybe not realistic though, for what we're dealing with right now. So once you finish that though, this is again going to be an exponential function. It's going to have the same form as the others that we were looking at. So we're still going to have this general exponential form, y equals a times b to the power of x, where a is the starting number, b is your multiplier. Sometimes they call this a growth or a decay factor. In this case, it's a decay factor because it's going down. So decay is just a word for basically a negative correlation in exponential form. Having like a negative slope in exponential form, they call that decay. That multiplier is now a decay factor. And x is again our independent variable. And that, in this case, is infection rounds. So on this one, notice the one that is going by 3/4, say y equals 80,000 times 3/4 to the power of x, because you're going 80,000 times 3/4, then taking that number times 3/4, that number times 3/4. So x is the number of times you've multiplied 80,000 by 3/4. The second set of data would be 80,000 times 1/2 to the power of x. So 80,000 times a half is 40,000, times a half is 20,000, half is 10,000. X is the number of times you've multiplied 80,000 times 1/2. The last one really drops steeply is 80,000 times 1/10 to the power of x. So for exponential decay to happen, it just means that that multiplier is less than 1, not negative. You'll see that in the Adromine modules. That multiplier can't be negative. That might be kind of an extension as we go into next week, understanding why you can't have a negative multiplier and still have any kind of a normal pattern. But it's somewhere between 0 and 1. So you multiply a number by a number that's less than 1, fraction, that number gets smaller each time. And so with this one, you'll have to do the same type of thing. Um, you can't you can't put in this equation and solve for x unless you get into some really advanced math. So you want to know when 80,000 times 3/4 to the power of x is equal to something that's less than 1. So on this one, you're just going to have to repeatedly multiply 80,000 by 3/4 or multiply it by 0.75 until you get to a number that is less than 1. So you'll have to get out your calculator, times 0.75, and you can just count how many times you hit the equal sign. See how long it takes for you to get to less than 1. And so you'll do that same thing with 80,000 times 1/2 to the power of x and 80,000 times 1/10 to the power of x. Just keep doing that on your calculator until it becomes less than 1, and that's when the infections would be totally gone. And if you think about it, the end, it goes really, really slowly towards 1 because that number is really hard to get to. Even with the flu, you have people who constantly a handful of people with influenza. It never totally disappears, and then it pops up again the next year and spreads in a slightly different form. So it does take quite a while, but that's what exponential decay does. It starts dropping really quickly at first. The numbers go down really fast, and then they slowly, slowly approach 0, but never quite get